The EBI Local Moran is the first way to deal with variance instability in rates. So the problem, as we mentioned, is that the variance of the individual proportions or rates at each location are not constant. So how do we fix that? There's actually been quite a bit of discussion of this in the literature. What not to do is just smoothing the rates the way we smooth them for mapping, and then applying the standard Moran's I, either the global or the local variety. So that's very tempting because we create these smooth rates initially, but the problem is that the smoothing induces spatial correlation, so you get a misleading effect of a misleading impression of spatial autocorrelation, which is really due to the effect of the smoothing and not due to the variable itself. So instead, the proper approach, is to adjust the Moran's I statistic directly. And there are a number of different ways to do this, to deal with this constant risk hypothesis. So in other words, we need a constant risk hypothesis to allow for spatial autocorrelation to work properly, but it's violated in this case. So how do we fix that? And the approach that we'll discuss here is the one used due to Asuncao and Reis, and it's really a fairly simple approach in that rather than smoothing the rates and then using those, you standardize them directly, but you use an empirical Bayes or EB logic. And so the standardization is the same as we've seen before many times. We create a new z variable, z at I, which is the original rate, minus a mean and divided by a standard deviation. Now, the mean is the same for everybody. The standard deviation is location specific. That is the catch. So we take each of the original rates, we transform them, and then we can deal with them as a standard variate. So we can do global Moran's I, local Moran's I, whatever we want. So the key is to make the transformation first. And this transformation technically is fairly complex, and we won't really go into the detail. I've included the paper in the reading so you can explore this further there, but the principle for the mean is very simple. The mean is basically the average, so not the average of the rates, but the average of the cases per population. So you sum all the cases over all the areas, and you sum the population over all the areas, and that ratio is the mean. By the way, this is also the same ratio that is used to get the expected count, which we've seen in the relative rates, and we'll see that again later on in the scan statistics. So the expected count is based on the average number of cases throughout the region aggregated. Then the variance is a little tricky, and first of all, the expression is fairly tricky, but there is one drawback with the variance, and the variance is the first term, and then you subtract the second term, and that's the problem, because sometimes the first term is actually smaller than the second term, which would give you a negative variance. And as we've already seen, negative variances don't exist. So what do you do in that case? And in that case, there are a number of different approaches. One is to just ignore the subtraction. One is to set it to 0. There are a number of these, and that's a little beyond what we cover. But you see that the variance is a complex operation that involves the populations and the rate at I and the total and average populations in the region. So you then take the square root of the variance, and then you're in business. So with these transformed variables, you carry out the local Moran statistic, for example, again using the school data in Nepal districts. We see the standard application of local Moran's I on the crude rate on the top, and the EBI Local Moran in the bottom, and there's only one district where it makes a difference in an additional spatial outlier is identified. In practice, or at least in my experience, I have seldom found cases where the effect is major. It's usually fairly marginal, but it may matter because these may be important locations. And as I mentioned before, the problem is going to be much more serious when you have truly small area analysis, where the areas are small and so their populations are small. And that's when you have a problem. When the areas are fairly large, like these districts tend to be large enough so that it doesn't really matter. Okay, so then the alternative is to use scan statistics, to which we turn next.